Cheating at video games. The reason I've been trying to teach all of this and what we'll be building towards over the course of many videos is cheating at video games. Not multiplayer video games. I don't actually want to go ahead and get banned or learn new things about my mother in chat. More like local games, small games, tiny indie labor of love. Like, this is how I work through trauma kind of games. I don't get the whole computer thing. We've been building these sophisticated machines that can automate anything, but for some reason we're still playing games by hand. Now that doesn't seem right to me. If I somehow could find a way to make the computer play games for me, that would free up a lot of time, which I could then use to make videos about making the computer play games for me. But as it turns out, there's quite a few moving pieces. So first I made messing with a recipe, in which we just go ahead and change what's in an executable file straight up, and then that changes its behavior because that's where the code is. And then I made computers as a social construct, which, if you survive through like 20 minutes of talking about numbers, essentially shows you what's inside executables is not random garbage. It's just arcane garbage. So now you've had two gentle introductions to the world of x86 machine code, so I'm just going to assume that you're basically an expert now. You can just wing it. So what I want to make is a program that can attach to a game and just sort of mess with it. Maybe read the image on the screen, figure out where different things are, simulate some inputs, things of that nature. Almost like a cheat engine. Okay, I know that this isn't breaking ground. There is a tool literally called Cheat Engine, which I've never tried, but you've got this backwards. Cheating at games is the excuse I'm using to teach you all about computers. So using a ready-made tool would defeat the purpose. The point is to write as much as we can by ourselves. Also using Rust, because I make the rules. And we're doing pretty well. We've done a thingy that overwrites at runtime part of the code of some applications. We're like 90% there. We just got a couple issues. One, all of this has been happening on Linux so far. Two, we used LD preload to inject a dynamic library into an executable at startup. That is a very different thing from attaching to a running executable and injecting some code in it. Moving forward, we need to think less terminal hacker ninja and more malware adjacent. And three, when we hooked the open function by overriding the first few instructions, we just ruined it. We weren't able to just come in, do some work, and then forward to the actual implementation of open because we didn't change the call sites. It's not like we found all the places that called open and had them called something else. That would have been fine. We changed open itself so that no matter where it's called from, it executes our code instead. But in doing so, we corrupted open beyond repair. It's never going to be the same again. It has our handmade x86 machine code that just returns 0, or it's just a breakpoint, nothing that would actually open a file. And that's a big issue if you consider that the functions we might want to hook to cheat at a game are related to showing stuff on the screen. If we don't call the actual function there, then we're just going to see nothing. And in this video, we're going to be focusing on not that. First, we're going to address the fact that we've been doing this on Linux, which was nice because I know the tools to examine executables and debug them a lot better over there. But I mean, I know it's 2022 and Wine has gotten a lot better and Proton is a thing and the Steam Deck is a thing, but Windows is kind of where the games live still. Sorry. Plus, I mean, it's interesting. You can install either Linux or Windows on the same computer and take advantage of most of the hardware in there. So they're similar in that way, but they're also different in a lot of interesting ways because they have very different histories and goals and design decisions. So first, debuggers. On Linux, we were able to use GDB to debug a program such as this one. That one just sleeps forever. If you run it, it just appears stuck. Hey, Editing Amos here. I'm saying this runs on Linux, but you can see that it's Windows 11. You can see the taskbar and everything. What's happening here is I'm using VS Code's SSH remote feature to remote into a Linux VM called Bobby that I have running in VMware somewhere on my computer. So you're only going to see the Windows 11 UI, but anytime it says in Bobby in the shell prompt, or it says SSH Bobby in the VS Code title bar, that means it's running on Linux. I hope it's clear. We're only doing the first part of the video on Linux and then the rest is Windows, just to compare what it looks on both operating systems. Okay, back to the video. So if you don't have the source and you want to figure out what's going on, you can attach to it with a debugger, proving that, yes, you can attach to a running executable under Linux. First, you need a PID, a process ID, and then you pass it to GDB and it attaches. And just attaching is enough to pause the target process. And from there, you can use backtrace or BT for short, and you can see exactly where it's stuck. That's the stack. It's the stack we were talking about in another video where you got thirsty and got a glass of water and then came back to the video. There it is. That's the stack. You can see the bottom of the stack is our main function. And then we got functions 1, 2, 3, thread sleep, and then the libc wrapper for the nanosleep syscall. And there's other commands like step and steppy, and you can set breakpoints and catch points for syscalls, and you can do a lot of fun things in the debugger, which is neat if you want to mess around with an executable just to see how it behaves. So Windows, how would that look like on Windows? Well, we got GDB on Windows too. But there's kind of a split world thing happening there where GCC, the C compiler, was ported to Windows several times. My favorite port is MinGW64, and you can build C programs on Windows, and you don't need compatibility layers like you would with MSys, but it does have a different format for debug information. It has a different API for C++, and just overall a lot of different choices. There are ways to call one from the other, but the general advice here is don't mix them. I mean, it's unavoidable because system libraries, but don't mix them in your application. So because I'm using the MSVC variant of the Rust toolchain here, which I want to do anyway because I'm teaching Windows today, if I ask GDB for Windows to attach to that process, it's going to be real confused. And we're not going to get a stack trace, just a bunch of question marks. So instead of using GDB, we want to use some tool that's designed for the MSVC API and debug in full format. In our case, that's going to be WinDebug Preview. Why preview? Because that's the most up-to-date version you can get. It is, according to some, the only reason to use the Microsoft Store. And now, everything's GUI. You don't use the command line anymore. You have a graphical tool with honest-to-God buttons and lists and everything. There's a handy attach to process feature, which I used to attach to our still stuck executable. And same as before, it's going to download some additional debug files from the internet, and then it's going to pause our process, and we're going to be able to take a look at where it's stuck. And just as before, we see main 1, 2, 3, and then a Win32 function called sleepx, and finally the NT-kernel syscall wrapper NT-delay execution. On Linux, that was nanosleep. And I don't know why that's so fascinating to me, the idea that you can write the same code and it will behave roughly the same on two completely different systems. The whole concept of cross-platform software has been an obsession for me for some reason, and I hope you can share some of the excitement. You can see in the toolbar there, we're also able to step out, in and over, break and continue, all your standard debugger stuff. And if we double click on one of our functions, we can see its source code because we built it ourselves, so we have that info. Also, I lied, because that's what I do. There's actually a command line right within the debugger, and that's how you do more advanced stuff that doesn't really fit in the GUI. And that covers debugging, but it doesn't explain how the heck we're going to attach to a running executable. Well, as often in the Windows world, there's an API for that. And since late 2021, there's a pretty good Rust crate to call any Windows API you can think of, because they all have a machine-readable description. So all they had to do was just generate some Rust glue code based on that. That's a load-bearing just. The team at Microsoft went through a bunch of iterations to improve the ergonomics of the whole thing, and now it's pretty good. Say I want to show a message box, for example. I can pull in the Windows crate, enable a couple features which correspond to the APIs that I need, and white string and color R for error handling because I like it. And then I can call message box W for white string. And this is all checked through the type system. LP text and LP caption have to be a pwstir, for example, pointer to white string. I can't just pass any old pointer. Similarly, utype needs to be a message box style. I can't pass any unsigned 32-bit integer. I have to use one of the constants like mbok, which just shows an OK button. And if you're wondering why use the wide version, W, rather than the NZ version, A, is because Windows is UTF-16 internally, so I'd rather use what's closest to the actual implementation. Since the Windows 10 1803 update, you can opt into the UTF-8 NC code page and just use A functions everywhere, but that requires either a system-wide registry change or an app manifest, which we're not going to bother with. Anyway, our code just works. We get a tiny message box. Yay! It's a little blurry, but that's just because of DPI scaling. Since I'm capturing this on a 4K display, I'm at 150% scale, and our dumb little executable is not a DPI-aware application. We could fix this again by adding an app manifest, but let's stay on task. It is time to mess with another application, one that's already running, so another process. Just to give you a mental model of applications and processes and threads, one application might have multiple processes running from a bunch of different exe files, and each process may have any number of threads. threads from any process can execute in parallel, and then it's up to the threads to synchronize between one another so you don't have race conditions where threads A and B are trying to change the same thing at the same time, or deadlocks where A is waiting on B and B is also waiting on A, and so they're all just waiting forever. On Linux, we'd use the ps utility to list running processes, and on Windows and PowerShell, we can use getProcess. Here you can see that I have Chrome opened, which has a bunch of processes. Let's review the columns here. NPM is non-paged memory, PM is pageable memory, here in megabytes, WS is the size of the working set, CPU is the amount of processor time in seconds, ID is the process identifier, which we usually call PID on Linux, and process name is the short name for the process. A process on Windows is a resource like any other, just like files, for example. You can open a process and you get a handle to it, just like a file descriptor, but for a process. And with that handle, you can, well, for example, you can query its full image name, not just Chrome, the short name. I'm talking about the absolute path on disk of the Chrome executable that's running. So let's make a program that takes a PID as an argument, opens the process, and then calls query full process image name W. Now, this isn't a Rust API, it's a Rust wrapped C API, so it's not returning a string or anything. It wants a buffer and its size as an in-out parameter. There's some invariants we have to uphold ourselves. If we pass a buffer of size 2, but we say it's size 10, then that function will definitely write outside the boundaries of that buffer. There's no mutable slice type in C. There are also no lifetime annotations, but here from that function signature, I'd say it's equivalent to us passing a mute stir, except it's UTF-16, meaning that we, the caller, own the string, and we're just passing a mutable reference to it long enough for query full process image name W to write to it. The length is also passed as a pointer to a U32 because it's both an in parameter and an out parameter. The input is how big the buffer is, and the output is how long the full process image name ended up being, not including the null terminating character, which we don't care about. We don't do C-style strings in Rust, we just do slices. But anyway, we also have to be careful about the output value because after the function returns, only part of the buffer has been written to. So if we read beyond that, we're just reading garbage, and that's not good either. Turns out there's a lot you need to know and be careful about when using those low-level C-style APIs. And this is all noise, it's not relevant to what we're trying to do. So you know what, let's make a safe wrapper for it so we can forget about the gory details. Okay, cool. That takes care of allocating 16 keybs on this stack. No, wait, 32 keybs because those are U16s, so they're 2 bytes each. Then it calls the Win32 function and converts it from UTF-16 back to UTF-8, which is what we want in Rust and everywhere, returning it as an own string that lives in the heap. It also does error handling. Any Win32 function that can fail has a return type that can be turned into a result by calling the OK function. It's one of the many nice ergonomics of the Windows crate. We don't have to remember if success is true or false or 0 or non-zero, and we never have to do those comparisons by hand. Now, the rest of the program is pretty straightforward. I like to use the R crate, ARGH, to parse command line arguments. We'll just have a positional U32 argument called PID. And then the main function is exactly as planned. Install the error handler, parse CL arguments, open the process with process query information, and query and print its image name. Now we can run it with cargo run. Of course, it wants a PID. PowerShell is actually pretty nice here. We can manipulate the output of getProcess if we wrap it in parentheses. Brackets let us access whichever element. We'll just pick the first, and then we can access a specific field. Here we want ID. And there we go. We've messed with another process. Well, not so much messed with it as just read some of its states. We can do better than this. We can create a remote thread inside of another process, which will then be able to execute arbitrary code. If that sounds dangerous, that's because it is. But here's a reason I like computers. There's no actual danger here. I'm on Windows 11 writing user space code. My computer cannot physically explode if I write something wrong. The worst that can happen is some process just crashes, which means it just stops. It's not going to be very impressive. On the plus side, that means we really have no excuse not to experiment because either we come up with something cool or nothing happens. The function we want here is create remote thread, and it wants a handle to the process we want to create a thread into. It also accepts a bunch of settings, the most important one being LP start address, the address of the code where the thread will start executing. In the Windows crate, the type of that parameter is LP thread start routine, which is an alias for option unsafe external system f and mute c void. Now that's a mouthful, but yeah, basically it's just a function using the std call API, the one that's used for system Win32 functions, and it accepts a single pointer to whatever. The value passed to that function is what we pass to LP parameter. This should be everything we need to inject some code in a target process. So let's give it a shot. As requested, we'll make an unsafe external system function accepting a mute pointer to c void. And from there, we'll just say hello. And then same as before, we just open the process with a little more access than before. We'll want create threads, a bunch of VM operations, VM for virtual memory, not virtual machine. Here, we're calling create remote thread with no particular attributes, the default stack size, the address of our entry function, a null pointer as its argument, no specific creation flags, and we're passing TIDs and out parameter so we get back the identifier of the thread that was just created. So, which application should we mess with? Let's take something that ships by default in all versions of Windows, Notepad. We can get its PID via getProcess, and pass that to our Rust program. What happens next will surprise you. Oh, that didn't seem to do much. Let's do it again. Oh, it crashed. I'm shocked. Shocked! Well, not that shocked. It's just like I promised. If we failed, not much is gonna happen. Nothing cool, but nothing too bad either. Here, Notepad just closes. Oh well. Still, I'm curious exactly what happened, which is good because I just showed how to use a debugger. So let's try this again. First we start Notepad, then WinDebug preview, then we attach to Notepad. Attaching to Notepad has paused it, it did a break, it broke, the broke point. Anyway, right now it's not accepting input, so we need to resume execution with that big green go button on the top left there. Let's see, if there's more than one battery on the bomb and the button says detonate, press and immediately release the button. I don't think I'm reading from the right manual here. So we press the go button and now Notepad works again. That's what we wanted, right? I forgot what we... Oh, right, the injection. So we do the same as before, which creates a remote thread inside Notepad and... Oh, WinDebug is trying to tell us something. What is it, boy? An access violation? Down at the lake? First chance. First chance exceptions are reported before any exception handling. The exception may be expected and handled. So we can see our new thread here. It's just not in any function that WinDebug knows about. And if we click go again, we get a second chance exception. If we keep clicking it, it just keeps going. It just never stops. So we messed something up. Which, I mean, the function is right here in the code for our injector. So why would WinDebug, which is looking at the process for Notepad, not see that? Ooh, I see what's going on here. They're different processes. We can't just, they have, so Notepad is over here with its own address space, right? And it has a bunch of libraries for user interface stuff. And our program's over there and has a different address space as well. Both spaces are mapped to physical memory, or maybe files or devices, or who knows. But the point is the addresses are unrelated. It's like they're different cities. Do you know how many Church Street there are in the UK? At least 7. And they're not the same place at all. So when we're holding a pointer or a reference to something, we need to qualify which process we're talking about. Which is a good thing, because that means we can't accidentally step over another process's memory just because we happen to have memory pages close to one another. 2 pages from different processes might end up being next to one another in physical memory, but that wouldn't matter, because if we tried accessing past the page, we would get an access violation, which is exactly what we're seeing here. Okay, so it's not enough to create a thread. The address of the start function must be from Notepad city and not from our program city, so we need to also remotely allocate memory in Notepad's address space and then write some code to it so that our newly created thread can execute it within Notepad's address space. There's virtual alloc x, which reserves, commits, or changes the state of a region of memory within the virtual address space of a specified process. That's exactly what we want. And then we'll have to put something in there, like, I don't know actually, that's a good question. I mean, when we did that on Linux, we wrote a small assembly program, translated it to machine code with an assembler, and then took that machine code and then just wrote it to memory. And Linux is so comfortable because every process has a standard input and standard output and standard error, and they have known numbers. And there's a write syscall, and it has a stable number as well, so you can just do this. But on Windows, there's no standard output. I mean, they implemented C, so they have recreated the concept of standard output on top of the NT kernel, but there's no concept of standard input in the kernel itself. What is this? Kernel for nerds? No, there's a whole console API, and you have to talk to the rest of the system, and there's a lot of things involved. It's not just one syscall with some well-known numbers. Also, syscall numbers change across Windows versions. You're supposed to use wrapper functions, not make syscalls directly. But the real question is, who's going to stop me? So let's see, I'm on Windows 11 build 22000, where the syscall number for NT terminate process is 44 decimal or 2C hexadecimal. The first argument passed in R10 is the handle of the process to terminate, and -1 means the current process. The second argument is passed in RDX, and it's the exit code. We'll just use 77 as a recognizable value. That syscall should never return, so we'll just add a HLT, halt, instruction in case it does, like if we've passed invalid parameters or something. I'll make a little just file, just like make, only simpler. Still using YASM to assemble, but targeting Win64 instead of ELF64, and emitting some debug info WinDebug can pick up on. Linking is now handled by the MSVC linker. We ask for debug info, the console subsystem, absolutely no libraries, and we specify our entry point, which is _main. And that works. What's our next step? Before we try injecting it into another process, let's try running it from our Rust application directly. So we want to disassemble the code to figure out what machine code YASM generated for us. On Linux, we'd probably use objdump, and on Windows, we can use dump bin, which ships with MSVC. Then it's just a matter of copying that machine code wholesale into our Rust code and jumping to it. We're not going to make the same mistake as last time. Before we jump, we need to adjust memory protections so it allows execution, not just reading and writing. And because there's not really a way to jump to an address in Rust without using inline assembly, we'll just pretend it's a function and call it instead. Yay, first time. And now let's do the same to Notepad. So all together now, we open the process with the right permissions, allocate some memory there, that's RWX, read, write, execute, write our machine code there with write process memory. Remember, we can't use memcopy, or rather copy from size here, because we're copying from our address space to Notepad's address space. And finally, we create a remote thread with the start address of the machine code we just wrote. Let's try it out. Here we're starting Notepad with the PowerShell command start process using the pass-through option, which gives us a process object. If we assign that to a variable, we can query its ID property, and that's the PID we need for our injector. So we pass it to our injector, and immediately Notepad exits. That's a good sign. Let's check the exit code, 77. Woohoo! So let's recap. Each process has its own address space, and Windows actually makes it really easy to open another process, allocate memory in its address space, write to it, and then create a remote thread that can start from any address in that space. There's just one problem. It's not really a problem, it's just I'm feeling lazy. What we've done so far works. We can definitely write some assembly by hand, and then compile its machine code, and then copy that machine code into the target process directly so that it can be executed. But I want us to do a lot more things in that target process, and I don't want to write assembly for every little thing we do. Plus, the code we wrote isn't really portable. Syscall numbers aren't stable on Windows. They can change between minor versions as of Windows 10. Not for NT terminate process, as it turns out, but that's just one of them. Plus, syscalls will only get us so far. At some point, we'll want to interact with other Win32 APIs, and we're going to need to be able to make proper function calls for that. And right now, It might not be obvious why calling functions is hard. Couldn't we just write function calls in assembly and copy that to the target process? After all, it's just machine code. Well, when you can't figure out what could possibly go wrong, that means it's time to try it. So let's have our assembly call the public documented Win32 function terminate process instead of making a syscall. I'm on a 64-bit version of Windows here, so calling convention says, by default, the x64 calling convention passes the first 4 arguments to a function in registers. The registers used for these arguments depend on the position and type of the argument. Remaining arguments get pushed to the stack in right to left order. Integer valued arguments in the leftmost 4 positions are passed in left to right order in RCX, RDX, R8, and R9 respectively. To make it work, we'll need to declare it as extern in our assembly file, and we'll need to pass kernel32.lib, the library that defines it, to the linker. And it works beautifully. I have a good feeling about this. Okay, so let's disassemble now and copy the code. There's in the code there's a lot of zeros. I'm sure it's nothing. It's probably nothing. Let's try it. Well, it did quit Notepad, but it didn't exit with code 112. Which, I mean, no, you know what? Let's pretend we didn't see anything and we are at a complete loss as to what in the world is happening with our program. How would we debug it? We could attach WinDebug to Notepad, but what would we break on? We can't break on the name _main because it's not in Notepad's symbol table. Remember, we're just brutally shoving machine code in its address space. It has no idea what it is. We could set a breakpoint by address if we knew what the address was. Okay, new plan. Let's have our injector print the address, then wait for us to press enter so we have a chance to insert a breakpoint in WinDebug first. There we go. Now we launch Notepad, launch our injector, set a breakpoint, resume Notepad, let our injector continue, and hey, there we have it. Let's just step through and we reach halt. Well, that's no good at all, but it is interesting. If we look at what the E8 opcode does in 64-bit code, it is a call near relative displacement relative to next instruction. And since the displacement was just a whole bunch of zeros, I guess we called the next instruction instead of terminate process. So that's fun. We have 2 problems here. One, relocations are a thing here too. Yasm, our assembler, has no earthly idea what the address of terminate process will be, so it just writes in zeros and leaves a note for the linker saying, hey, please replace that with the actual address when you get a chance. Okay, hon? Problem 2. Kernel32.lib does contain a definition for terminate process, but it's just a thunk that calls the actual terminate process from the shared library kernel32.dll. I know because I disassembled the executable itself. It's the same code, just after relocation. The displacement here is not 0, but it's also mighty suspicious. It's just hex 1007, or decimal 4103, almost the size of a page. And if I keep scrolling the disassembly here, we find the thing it's calling. And that's not the actual implementation of a terminate process, it's just a thunk. For every symbol that we import from a shared library at DLL in Windows, there's a thunk that jumps to the value of some global variable. When our program is loaded, when it starts, all imported DLLs are loaded as well, and all the symbols we imported are resolved. Their address is written to those global variables. And so we're in a bit of a pickle, because we don't know the address of the actual implementation of terminate process in Notepad's address space. We don't even know if it imports terminate process or even kernel32.dll. Okay, probably does. It seems unlikely that Notepad is using raw syscalls like we did before, but still, we have no idea what the address of terminate process is, and even if we did, we'd still need to compute the offset of it relative to the address of the next instruction, which is halt in our case. Also, because we only have 32 bits to express the displacement, it has to be within 2 GB of holds, either direction. Actually, let's check that first. Let's ignore the fact that terminate process might be at a different address for our program and Notepad, and just print the address of terminate process from our program. That is not within 2 gigabytes at all. Those are 137 terabytes apart. But wait, which terminate process is that? Is that the real one, or is that the thunk? I bet it's the thunk. We can find out by attaching WinDebug to our program and disassembling from the address we got using the U command for unassemble. Look at all those jumps. Those look like thunks for sure. We could have used the ln command, list near symbols, instead, and that would have told us that we're looking at our program's terminate process. WinDebug shows the qualified symbol name, module name, exclamation mark, and then the symbol name. We can use the question mark command, evaluate expression, to show the address of the global variable that's supposed to hold the address of the real terminate process. But wait, that's just the pointer. We need to dereference it. The question mark command accepts MASM syntax, the Microsoft assembler, and in MASM we can use poi to dereference a pointer. To find which symbol that is, we can use ln again, or actually we can use ln in conjunction with poi and the symbol name. Look at us learning WinDebug. Aha! Finally something in kernel 32, but it says stub. Is that another stub or thunk? Let's disassemble it. Gosh, yeah, it is. Well, rinse, repeat. Okay, now we're in kernel base. Interesting. Is that yet another thunk? No, it's not. That looks like a real function. Okay, let's regroup. So we tried injecting some code into Notepad that called out to terminate process, but there's 2 problems. Problem number 1, we copied the code from the assembly of an object file, .obj, and that one calls to an address that's all zeros, since relocation hasn't been performed yet. And because the call instruction used is relative to the position of the instruction pointer, we ended up jumping to the next instruction. Problem number 2, even if we copy code from the assembly of our executable file, .exe, the address we're calling out to is still wrong. It's the address of our program's thunk for terminate process, which just ends up calling kernel 32 stub for terminate process, which in turn calls kernel base's real implementation of terminate process. So, if we want our injected code to be able to call terminate process from within Notepad, it has to call one of 1, Notepad's terminate process thunk, 2, kernel 32's terminate process thunk, or 3, kernel base's actual terminate process function. And the question is, how the heck are we going to figure that out from outside the process? And who's to say Notepad even has a terminate process thunk? Not that we'd know how to find it, but does it even have one? Maybe it works completely differently. I think we need a second WinDebug session. Okay, so attaching to Notepad, let's look for something in kernel 32 that starts in terminate process. Yeah, see, there's the same thunk. And you know what's even better? It's at the same memory location for both our program and Notepad. And that's because some DLLs, like kernel32.dll, always load at the same base address for all processes, which is lucky because now all we need to do, and I know I say this a lot, but all we need to do is to find the address of kernel 32's terminate process thunk from our program, and we can inject it into the other program, and it'll just work. So how do we get that address? Well, importing DLLs is just one way of using them. We can also use load library to open them at runtime, and then we get a handle, which we can use to look up symbols. Do you see a pattern here on Windows? Everything is a resource, and you can open them, and you get a handle. Here, kernel 32 is already loaded in our program because we depend on it. So instead of load library, we can use get module handle W for wide. That's another feature of the Windows crate. Thankfully, those are listed in the Rust docs that Microsoft published, so let's add it real quick. Now we need to pass a UTF-16 string as the module name because I insist on using the wide version of all these functions, even though it's all just ASCII names anyway. But there's a nice crate for this. There's actually a couple. We'll use U16 CStir. Hey, we did it. Well, sort of. Now, we have to put that address into the code we're injecting into Notepad, which, no. We shouldn't put that address exactly. It's a relative jump, remember? And we can only specify a 32-bit offset. And the problem is we can't jump over that gap. It's too big a gap. Where does the address of our code come from anyway? Who chose it? Well, it's the OS, it's Windows. We just made a call to virtual alloc x, and because we passed null as the LP address parameter, it just picked something anywhere that was free. But actually, we want our allocated memory to be close to terminate process, within 2 GB of it. So we can't let Windows pick. We can't pass null as the LP address parameter. We have to pick something ourselves. But it can't be memory that's already used for something else. Actually, now I'm curious. What happens if we pass the address of terminated process itself? Is it going to overwrite the memory? Is the call going to fail? I genuinely do not know. So let's try it out. Okay, it failed. I was scared for a second that it was just going to succeed, but so we just need to find the next free page of memory after terminate process. First step, find how large the memory area that contains terminate process is. And now that we have that info, we just try to allocate right after that, I guess. Take the base address at the region size. It didn't work. I guess that one's taken too. Well, we could just loop to skip over all the regions until we find one area in memory that's free. Still failing, huh? I don't love the error handling here. We're just checking that virtual alloc x doesn't return null, but we don't know exactly what went wrong. We really should be calling getLastError to know more. Error 87. I don't have a list of all Windows error codes in my head, so let's call format message to translate that to something a little more human readable. We'll just add the white string crates and... Okay, the parameter is incorrect. That's really illuminating. Let's take a closer look at the output here. That last region seems significantly larger than any region before it. It's almost 30 gigabytes. I don't think we need that much mapped memory. I must say that I genuinely don't know what I'm doing. That's the risk of writing these videos as I'm researching them, so I'm just making guesses here. What I'm seeing is that the page type is 0, the allocation base is 0, and the state is, I don't know what that value means. That's mem-free, it's free memory. So when I researched this, I actually found that there's free memory before that. It's just that the last region we find is all the rest of the free memory for this process, and I guess that's why it's suspiciously close to 32 gigabytes. But the free ranges before that may be too small, and we'd have to care about alignment and all those things. It would take some effort to write correct code there. So instead, we're just going to do the easy thing and just pick from that last ginormous free region. While testing, I found that allocating at the base address of that region didn't always work, so for safety, we'll leave a margin of 64 kbps. And now the distance between our code and terminated process is less than 2 kB. We're not computing the correct distance though. Never mind the fact that I'm pretty sure our usage of offset from is undefined behavior. The relative jump displacement is between the address of the next instruction and the address we want to jump to. So to find the proper offset, we need to determine where the halt instruction will be. It's not that hard, it's just kind of annoying to think about. It worked? It worked! Ah! Let's summarize. We wanted to attach to a running Windows process and mess with it. We found that Windows lets us allocate memory in another process's address space and create a remote thread that executes any instructions we wrote to set memory. We then tried copy-pasting some machine code that called terminated process and used WinDebug to notice that actually the call that was generated was using a 32-bit RIP relative displacement relative to the instruction pointer relative to the address of the next instruction, and that it called a thunk that definitely did not exist in the target program. And that thunk exists because our assembly program imported kernel 32.dll, and so it needed some place to jump to that reads the actual address of terminated process from a global variable that's filled at process started by the dynamic linker. But that thunk ended up calling another thunk from kernel 32.dll, and that one we can pretty sure is present in any Win32 application we hook into, and as a bonus, kernel 32.dll is loaded at the same address for every process. It actually changes on reboot, which I'm not going to show because do you know how many things I have running on my computer right now? So all we had to do was make sure that our injected code lived within 2 KB of the terminated process thunk from kernel 32.dll so that we could fill in the proper displacement for the call instruction. And doing all that, I think, is an achievement. I mean, we are about to discover that there's a much simpler way to do basically the same thing, but what a journey! I feel more comfortable doing code crimes on Windows now, even though I initially learned most of this stuff on Linux-based systems. So before we tear down most of our code, let's just take a second to appreciate the effort here. Okay, how do we make that simpler? Well, do we have to use a 32-bit relative call instruction? I've looked, and there doesn't seem to be a form of call that just accepts an absolute 64-bit address. But there is one that calls a 64-bit register. So if we just move our assembly around a little bit, say we move the address of terminated process into an unused register like R15 and then call R15, it still works. So maybe we can just use that. And then our code could be anywhere in memory. It doesn't have to be within 2 GB. Heck yeah. But why stop there? We've discovered that kernel 32 is always loaded at the same base address, and that means that when we create a remote thread, we can just have it start at any kernel 32 function we like. We can even pass one argument. And wouldn't you know it, there's a function in kernel 32 that loads some code and takes only one argument. Load library. W, still going for the wide everywhere thing. Its argument is the path on disk of a DLL. So instead of writing machine code directly into the other process's address space, we could just be writing some Rust code, compile it to a shared library, a DLL, and have the freaking dynamic linker loaded. And DLLs have constructors, so we can run code when it's loaded. Okay, so let's make a quick library. Check that it works. Yeah, it does. And now, here's the game plan. Allocate some memory in the target process, write the DLL's path to it, and create a remote thread that'll start in load library W, passing the address of the DLL's path in the target process's address space. Because we have no idea what the current working directory for our target program will be, we'll want to pass an absolute path to the DLL, not a relative path. Yeah. Isn't that much easier? And now we can write arbitrary Rust code. So we can make Notepad do anything. For example, we can make it show a message box. And you can tell just by looking at this that the message box comes from Notepad because it's not blurry anymore. Notepad, being an official Microsoft application that ships with Windows 11, is high DPI aware and so it scales correctly. So there you have it. We did it. We've successfully injected Rust code in a running Windows application. We've acquired great power and none of the responsibilities. Our only question moving forward is this: how can we have fun with it? Ba 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 beep boop.